Okay, in part 3, the remaining example says to use your knowledge of area and information pertaining to the fact that 0 to pi of sine x dx equals 2 to evaluate each of the following. So let's remember something about our sine curve. From 0 to 2 pi. Half of that's pi, pi over 2, and 3 pi over 2. Let's go up here. That's okay. The beginning, middle, and the end are 0, up at 1, and down at 1. And there is our sine curve. One would definitely say that the area from 0 to 2 pi is 0 because you got the same area above from 0 to pi as you got below. And remember that this graph would extend. This would be negative pi over 2, and this here would be negative pi. So then this would be the sine of negative pi over 2 is negative 1, and so it would continue like this in that direction to negative pi. So we're to use the fact that the value of the definite integral from 0 to pi of sine x dx is 2. Let's use that to find each of the following. Number 13, the definite integral from negative pi to pi of sine x dx. Well, I kind of cheated a little bit because I used the graph. I could use the graph if I wanted to. I could see that from negative pi to 0 of sine x dx plus 0 to pi of sine x dx would give me the definite integral from negative pi to pi of sine x dx. I can add definite integrals. Negative pi to 0 of sine plus 0 to pi would give me sine. Squeeze these together, I get it from negative pi to pi then. It's like this. If I'm going from negative pi to 0 and then from 0 to pi, that would give me from negative pi to pi. Well, if from 0 to pi is 2, and using my knowledge about the graph of sine, then negative pi to 0 would not be 2, but negative 2 because it lies below the x-axis. If I add these, I would get 0. And that's what my logic would tell me from looking at the graph of sine from negative pi to pi. In number 14, the definite integral from 0 to 2 pi of sine x dx. So if I go from 0 to pi of sine x dx plus pi to 2 pi of sine x dx. Well, from 0 to pi, I know that part is 2 from given. And what would be from pi to 2 pi? Well, since I got the same area below as I got above, then that area would not be 2, but would be negative 2. And if I were to add them, I would get 0. In number 15, we got the definite integral from 2 to x plus 2 of sine of x minus 2 dx. So what to do is, since you're given information about sine x dx, we're going to do a u substitution and let u be equal to x minus 2, the inside stuff, and du equals dx. So this would become my du, and this would become my u. Now for the first time, we're dealing with limits of integration here. So these two have to change. So this is when x is 2. When x is 2, 2 minus 2 is 0. So u would be 0 there. And then here, when x is x plus 2 right here, I'd replace the x with x plus 2 minus 2. These drop out and I'm left with x. So then this here would become oh, it's pi plus 2, not x. I thought something was funny. So it's pi plus 2. I wrote it down wrong. So it's pi plus 2. So x here is pi plus 2. So then I put in pi plus 2 minus 2. These drop out. I'm left with now pi. Okay. So that becomes the definite integral from 0 to pi of sine u du. which will be equal to the given information of 2. See, this is why we call this a dummy variable, because as long enough these change accordingly, the definite integral is going to be equal to the same, whether it's in terms of x or u, it's going to be equal to the same. Whether we did this in terms of x or in terms of u, it would yield the same answer, and that's why we call the variable there the dummy variable. In number 16, you got the definite integral from 0 to pi of 2 plus sine x dx. Always split things up at pluses and minuses. So I can split this up from 0 to pi of 2 dx plus 0 to pi of sine x dx. The definite integral of a constant is the constant times the upper limit minus the lower limit, which would be 2 pi. This by given information is 2. So the answer would be 2 pi plus 2. In number 17, the definite integral from 0 to 2 pi of sine of x over 2 dx. If I choose u to be x over 2, du would be equal to 1/2 x. Put a 1/2 in, take out a 2. This would become my du. This would become sine of u. And now the limits have to change. These have to change because the limits here are in terms of x. They now have to become in terms of u. So when x is 0, I get 0 for that. And when x is 2 pi over 2, these drop out and my answer is pi. Again, we call this a dummy variable. Whether this is in terms of x or u, it's going to be equal to the given information from 0 to pi of sine x dx, which is equal to 2. What you can realize here is this, the sine of x over 2, its graph, the period is being doubled because sine is bounded between 0 and 2 pi and sketching one period. So if we multiply everything by 2, we'd be going from 0 to 4 pi then, would be one period. So it's getting, the period was actually lengthened. So you can think about that too in applying some of these, but it's just easier to just do the u substitution. And finally, number 18. In number 18, the definite integral from 0 to pi of 2 sine x dx. So we can pull out any constant out in front and make it 2 times the definite integral from 0 to pi of sine x dx. And from 0 to pi, that value is 2 times 2, which is 0. 2 times 2, sorry, which is 4. Which is 4, thinking ahead of something else. Okay, also let's think about this, with this going on up here. We know that sine and its reciprocal function cosecant are the only odd functions. So remember that sine of negative x equals negative sine x, and its reciprocal function cosecant. So cosecant of negative x equals negative cosecant of x. They are odd functions. Opposite x's yield opposite y's. Opposite x's, negative pi over 2 and pi over 2, yield opposite y's, 1 and negative 1. So one could say that when you split them up with what they're symmetric about, which odd functions have origin symmetry passing through the origin, so it's going to be broken up at 0. So if you have an odd function, like in this case, the definite integral from, just call this negative a to 0 of my function f of x dx plus 0 from the origin to a of f of x dx will be equal to 0 when f is odd, because of the fact the origin is what splits up the areas to where you got the same area above as you got below, and when you add them you're going to get 0. So when you have a function that's odd, splitting it up at the origin means you'll have 2 equal areas where you get the same area above that's positive, same area that's below that's negative. When you add them, you'll get 0. Now remember, cosine is an even function. And, well, sine and tangent are also odd. All the functions are odd except for cosine and its reciprocal function secant. They're the only even functions, cosine and secant. So if you think about this, like y equals x squared, which has got the y-axis symmetry, that means the y-axis cuts it in half. So from negative a to a, and we're breaking it up, say at 0. Well, I got the same area from negative a to 0, when y is 0, as I got from 0 to a. So the area from negative a to 0 of f of x dx plus the area from 0 to a of f of x dx really just equals twice the area from 0 to a of f of x dx when f is even. It makes sense because you got two equal areas where the y-axis cuts it in half. So if it's odd, the sum of the areas will be 0. If it's even, it's the same thing as taking one of the areas and doubling it. So something else to think about and I'll be working on as we continue throughout this chapter more.